So I'll be presenting the outcome of this workshop that I organized with Leif Karlstrom and myself last year, and it focused on modeling of migration of fluids in subduction zones. And here I'm including aqueous fluids and melts as fluids collectively. And this is going to be, summary of community perspectives on general effort in modeling fluid migration. And it's not going to be, I won't be focusing on particular models or particular processes. And this is a part of a community effort through MCS RCN. And for those of you who are not familiar with MCS, it stands for Modeling Collaboratory for Subduction. And the objective of this collaboratory is for community and numerical model building. And it is really motivated or driven by this multidisciplinary data in subduction zones, and particularly in earthquake and volcano systems. We have this variety of data, and the processes that we want to study are inherently non-linear and transient, and we really need to integrate all available observations to really fully understand what's happening. So the objective is to build a modeling framework for multidisciplinary data integration. And MCS is also hoping to provide, through this framework, we can provide open and reproducible collaboration across the earth science community. And that should also lead to expansion of computational geoscience and STEM capacity building, which was discussed during the panel discussion yesterday. So there are a multitude of processes that are happening in subduction zones. This is demonstrating the global scale to lithospheric scale to smaller scale processes. And the challenge that MCS needs to address in building integrative modeling framework is really addressing how we can link these multi-scale, multi-physics processes. It's challenging, but this will lead us to a better understanding of the dynamics of subduction in general, and also earthquake and volcano systems in particular in that hazard context. So MCS RCN, MCS is in a planning stage. It is funded by NSF Research Coordination Networks program. The effort is led by Thorsten Becker and the steering committee. And what we are trying to do is to develop a plan for building this integrative modeling framework. And through a series of workshops and webinars, we had 2 workshops so far, one on fluid migration that I'm discussing, and the other on megastress system. And we have the last one next year, probably in late spring to early summer. The format is to be decided, but it's likely to be a series of mini virtual workshops spread over a couple of months, and hopefully a small in-person meeting. So if you're interested, please visit the website. So the workshop that we organized happened early summer last year, and it involved a lot of people. We had great members on the committee organizing and writing a report writing committee. So again, the material I'm presenting is based on the workshop, and also an article that Leaf and I wrote for EOS, which focused more on the challenges and opportunities in modeling fluid migration. So, one of the reasons why we decided to have a workshop on fluid migration before, focusing on earthquake and volcano systems was that we recognize fluid migration being an integral component for many processes, if not all, in subduction system, going from hydrothermal activities, earthquakes, melt generation, mantle deformation, landscape evolution, and volatile cycle. And fluid migration, and probably for most processes that we study, is remodeling, is done in an isolated for a specific domain within the system. So here, this diagram is simply illustrating that we have a variety of models that are being developed to study a specific aspect of fluid migration. And sometimes for a given domain, we have several different models, again, looking at different processes due to difference in scale, both temporal and spatial scales. So again, generally the domain is based on the temporal and the spatial scales of the process or fluid related processes that we are trying to understand. Now this, this is showing a whole diversity in our efforts, and this is a healthy thing that we should continue. But at the same time, if we want to achieve some more comprehensive understanding of the system, in this case particularly fluid migration, then we really need to coordinate all these efforts together. So the objectives of the workshop, this is not necessarily the objective, but it was really important for us to invite diverse groups of scientists to evaluate the current state of our understanding and identify any gaps in our models or knowledge so that we can coordinate again the efforts in modeling various processes that control fluid migration. And based on the discussions, we hope to build a community plan for integrative modeling framework specifically for fluid migration. So we did invite diverse groups of scientists, and the topic here is modeling, fluid migration, but we also invited observationalists who are also on the organizing committee, and we did have large modelers as keynote speakers. And this is also simply to illustrate the diverse groups that we had at the workshop. And so, prior to the workshop, we asked the participants to indicate the spatial temporal scales that they work with for their fluid-related project. And, scale going from less than 1 millimeter to more than, tens of kilometers here, so spatial scale and temporal scale, indicating that there were people working on various aspects of fluid migration. So I have a few discussion points that I would like to discuss, but before going into that, I just want to indicate general community consensus, again, on the current efforts in fluid migration modeling. Now, participants generally felt that the thing that we need to work most on is simply understanding the process that we are trying to model. The processes that control fluid migration. And again, on this, the diagram is a poll that we took prior to workshop, asking, what do you think is the most thing that we need to work on? And we had, simply understanding or incorporating, or how to incorporate physical processes into models. And again, another point is that participants felt that, we talk about interfacing models, but it's really interfacing modelers or scientists that is important. And also, we really need cross-disciplinary training where we, diverse people can meet and discuss and share knowledge. And this includes for both, scientists and students and all range of scientists. So this is partly, really emphasizing the need for community building. And in terms of the modeling, to move forward with fluid migration modeling, we need to identify and resolve common challenges, given that there's a lot of efforts happening, so it's rather fragmented. And to put this together, to coordinate this effort, we really need to identify common challenges, and also to provide approaches for model validations, not simply just building them, but how would we validate these models? So those are the things that came up frequently throughout the workshop. We did have a small, a short, I should say, early career scientist discussion separate from the main workshop, and there were certain things discussed, and I just choosing a couple of them that are relevant to this workshop. So what are the new numerical challenges in multiphysics and multiscale modeling? And modeling, multiphysics, multiscale modeling itself, it is a challenge, but within it, what would be, the challenges? And there are quite a few different things, but linking physical and chemical processes was definitely one of them. And I think that's, this echoes what Nadia was saying, this really example would be deformation and fluids, but with okay, so that's slightly different, sorry. In many models, with fluid migration models, we do not have chemical reactions included. And the other thing is the uncertainties in our knowledge in the processes, again, that we want to model, and therefore in the equations. So those are the challenges that they discussed. And how do we compare these the modeling results with observations? And I think yesterday could have been John Herland. Our models are nowhere near being predictive, but even then we could use models that are partly constrained by observations to predict what kind of observations are needed. So here we, iteration between models as predictive tools and observations as constraints. So we, what they were talking about, going back and forth, repeating this process to such that it will lead to a better understanding of the process and process. So again, just a few discussion points that I want to mention. When we talk about, so this is through the main part of the workshop. And when we talk about integrative modeling framework, some people might think about this grand model that, incorporates all sorts of, processes. Is that something that we will like, or is it still appropriate to model, each domain separately, as has been done? And so the general consensus was that a holistic model is probably not necessary or possible at this stage, and that a modular so Lego brick approach is appropriate. But in this case, so, we again model individual domain and then link them together, right? So that's great. So how do we link these models together, or domains together? And there are different ways of approaching this, but one of the potential way is to use output from one model to as input for another. So another possibility would be simply to couple models for models of neighboring domains, right, or overlapping domain. But instead of coupling the code themselves, we could use output in basically transferring input output. And even then, this seems it's not clear which approach is technically simpler, but this using output and input approach also comes with some technical issues. For example, if you have processes that are at different scales, right, but overlapping in space, how do you use one output as input for another? So in studying this, using this type of approach, it will be useful to know if there are common or dominant fluid migration pathways. So we wanted to see if the participants saw some common pathways, and there were some that people generally agreed on, but it was difficult to know which process or which pathway is more important. Basically, we can't compare currently available models to assess this because of different assumptions and parameterizations that are being used. So that would be that is another challenge that we face in understanding fluid migration. So somewhat similar question, what are the essential elements of fluid behavior across different domains? So if we can identify these elements, so when we talk about elements here, I'm referring to, maybe the rock rheology. It could be the chemical components, physical properties. They're essential, common components that are basically critical for fluid migration. And in general, yes, all of these are important, but there are no a set of elements that the community agree on. So what we came up with is this zeros order model that contains basic essential elements that the community can agree on, and that would be a good starting point. And lastly, what observations are most significant or needed. And we talked about a range of observations, seismic to geodetic to MT data, but people emphasized on among given these data, but we really want high frequency time series data. And particularly looking at transient processes, fluid related processes, and some other data or observations are those that can constrain equation state for non-pure hydrothermal fluids, and analog models. So these are really what I just discussed are more of the challenges that we will face in building this integrative modeling framework, which requires really community effort, organizing or coordinating various efforts. And in doing that, we believe it's important that we have common objectives. And so we propose in the report some motivating questions that sort of encompass, the broad interests of broad community. And so the one of a set of them were on this spatial temporal variations in seismic and aseismic activities. And one example was how, where, and where how, where, and when are elevated pore pressure, fluid pressure generated and maintained. And this is related to, small scale processes, and how do they relate to the wide range of interface sleep behavior that is observed at larger scale. And so here's the link between small scale and large scale that really need to be studied together. Another question would be, how do porosity and permeability evolve with matrix deformation? And there are some models that addresses these questions. An example is by Russ et al. Showing this evolution of localized flow. But more effort is needed, particularly placing this type of model in the subduction tectonic context. So having the background, incorporating the background processes that interact with fluid migration at this scale. A similar set of questions were raised on magma ascent. What processes determine the spatial distribution of magma, and from wedge to surface. And again, here we have a model by Ruber et al. That indicates the magma ascent from the top of a asthenosphere to the surface. And so this is a lithospheric scale model, but what we are still missing is the interactions between different elements of this within this system that basically controls the fine structures of magma systems, where the magma end up being at the surface. So that's coupling large scale to small scale models, and the opposite is true. This is model for Kilauea eruption for 2018 Kilauea eruption, and this is showing this part of the caldera just collapsing, and this type of phenomena or process cannot has not been really captured, right? Cannot be captured in large scale models. And lastly, how are fluid related processes linked to thermal, chemical, mechanical structure. One of the key questions that came up over and over was reactive transport or fluid mediated chemical reactions. Now when fluid migrates through or liquid migrates through solid, then it will cause thermal, chemical, mechanical disequilibria that really drives further chemical reactions and phase change. So incorporating that, how would that affect fluid migration? And also how does fluid migration affects large scale thermomechanical structure? So we have a model here for mantle wedge where it incorporates mantle flow, as this is a steady state mantle flow that is not affected by the fluid migration that is indicated by this color. Similarly, no melting is included in this one, and therefore no reactive transport. And so to discuss, there are many challenges we have, and we wanted to group them in certain way such that it's easier for us to discuss. And so Leif and I worked on this, and there are four groups that we recognize. One is resolving model commutability at different lengths and time scale. So example of a problem would be, how elasticity and brittle behavior of shallow material be represented in large scale, in this case, magma migration model.
Ikuko, I'm sorry to interrupt you. I'm keen that everybody gets a break, and I hate to interrupt such a great overview, but is there any chance you could finish up in the next minute or so, or two?
Yes.
Thank you very much.
Do that.
I'm sorry.
Yeah. No, it's okay. So This is also summarized in EOS article, achieving consistency among models, identifying commonalities in the problems, addressing the variability in the observational completeness. I want to emphasize that we have a lot of observations, but the completeness or availability is not uniform. Some problems have more observations than others. So how do we deal with that? So, the Modeling Collaboratory could provide, this modeling, integrated modeling framework, but also research environment for community building. And again, these are things that the collaboratory could provide. And hopefully what we envision is, MCS providing, some or help to unify these efforts that are happening in other modeling centers. And again, what I'm presenting is all in the report and EOS article. And I, if you can, I encourage you to read them. Thank you.